So welcome everybody. I'm going to talk about how to use Java streams to access existing data with ultra-low latency. And what is ultra-low latency? Yeah, that's something we're going to see later on in the presentation. I'm Per. I work with speed, so people sometimes have difficulty understanding my name. So I just say miles per hour, and then I know I'm Per. So it's easy to remember. This is my third startup. I've invented a lot of stuff. We're working with Java since 1.0. Lives in Palo Alto, and I have a Java blog called Mimbor's Java Pot with over millions of reads. So if you're interested in Java, you can go there and learn some stuff. Well, that's me. You can see me live here. That's better. So I'm going to talk about speed today, the need for speed. Everybody, every developer wants their application to run fast, of course, everybody. And when I ask people, why is your application not fast? They're blaming the users. It's the user's fault. They're running complex queries, or they're running this, they're doing that. But I think that we developer has to take some responsibility too. So we all know what speed is, but let's talk about what's not speed. What's the inversion of speed? And it's this. I mean, we hate this. It's not good. So what can we do about it? And why is it bad? Well, it's a bad user experience. There's been a number of scientific experiments carried out on users and how they perceive delays. And it turns out that about 100 milliseconds, people think that that's direct, that's instant. You can't notice anything less than 100 milliseconds. And if it's 1 second, we seem to perceive the delay, but it's not that really annoying. But 3 seconds is very frustrating. In one particular investigation, 57% left the site. And I know if you get 10 seconds delay, then you start about thinking about other things. You start about thinking your kids or school or whatever. You're not there any longer. So, I'm sorry. I jumped. So this is going to be an experiment, and don't take my word for it, experience yourself. So what I'm going to do now is an experiment with you all. And when I click here, time starts, and when it's ready, a kind of funny figure pops up there. And you can get yourself a feeling how long time it is. So we start with 100 milliseconds. So I click here, and there it is. Not that annoying. It's very good. So what about 1 second? Here's 1 second. Click. That's okay. Here's 3 seconds. Click. This is not okay. And 10 seconds now I clicked. This is a disaster. You don't want to present an application to a user that takes 10 seconds. It's a failure. And then you look at that. I don't know what this guy ate, but he looks funny. So, and what about costs then? Okay, it's fun if it's fast, but what are the costs if it's not fast? So Google, they made an investigation, and they lost 20% of traffic with half a second delay. And 20%, that's a lot of traffic for Google because they have a lot of traffic. Amazon did another experiment. They lost 1% of sales for every 100 milliseconds delay. So delay is a cost. It's costing you and your company money. Then you have higher overhead, of course. If things are taking a long time, you're locking up your database, you're allocating resources on the application servers, and the slower it gets, the more resources you need. So it's a kind of a vicious circle. And it destroys your brand. Suppose there is a bank and you're doing some kind of transaction, and the paying takes too long, you kind of lose the trust. You don't want to use that service. You wonder, does it work? Can I press resubmit, or what's happening then? So you kind of destroy your brand. Okay, so far I've talked about time frames that we as humans understand. We humans live in the middle world. We see stuff like this. This is a medium-sized object, and 1 second is the medium-sized time frame. But if we scale things now 1 million times smaller, 1 million times faster, that's the ratio between the sun, that's here, and this tiny, tiny little dot where we all live, called the Earth. So that's the scale now I'm talking about. I'm not talking now about 200 milliseconds. I'm not talking about 200 microseconds. I'm talking about maybe 200 nanoseconds. That's the time scale we're going to shrink down to right now. So what are those areas where speed matters? For example, in the fintech areas, you have something called high-frequency trading, where the person who can do the fastest computation wins. Actually, it's better to don't compute and don't do anything if you're not the fastest guy, because then you will lose money. But if you're the fastest man, you will gain money. And that's the same in the fintech area. The value of the information decays very rapidly over time, so you want to be fast. Another area is AI, where you can, instead of having your neural network take care of everything, you can compute things and inject that as a parameter in your neural network. You can gain speed, and you can gain training speed in your network, and you will have better results. And IoT, if you can look at a huge range of parameters, you can perhaps detect that thing going broken if you can do things faster. Whereas if you couldn't do that for speed reasons, then you might not even see that before it's coming to you. Defense intelligence and situation awareness. Well, if you can detect something 10 seconds before your enemy, that's of course can be a matter of life and death. The difference between success and catastrophic failure. Logistics, if you have a huge amount of spare parts, or if you have some kind of network you're planning, you want to be able to compute huge amounts of data quick. Science applications, space, DNA, of course, are some other obvious. Microservice architecture is a very particular need of speed, because you often have a chain of microservices and they all add up. So you want each microservice slice to be as fast as possible. And of course, in general computing, if your batch job terminates 10 times faster, then you pay 10 times less for that to be computed. Okay, so these translate to a lot of requirements. Low latency, that's what I'm going to talk about today, but of course it's important that it's deterministic, meaning that you can really rely on it. Low memory footprint, low CPU utilization. You don't want to create objects while you're using your services, so that's called low memory pressure. You want to make it parallel, so you can parallel your queries all over. You want to have the capability to scale out. So those are other requirements. But let's focus on latency. Why is latency so important? Yeah, because this picture shows kind of the real world we're living in. Things are complicated. You don't usually compute one thing and then you're ready. You compute one thing and then you go to the next stage, and then to the next stage, and to the next stage, and it goes on and on and on and on like this. And that's the reason why each step has to be so quick. Otherwise, they all add up. So let's just break down the latency requirements. So the thing is that it all adds up. Excuse the pun, but that's the way. So if you have, in a simple case, you have the total latency, which then is the sum of all steps. And maybe you have millions of steps before it completes. You remember this picture. This is complicated, millions of steps. So that leaves us with not so much time for each operation. Maybe we need operations that can complete in well into the nanoseconds, 200 nanoseconds. And what is 200 nanoseconds? Let me illustrate that with this piece of paper. This is a standard letter paper in the US, and in the rest of the world, you're using something called A4, which is about the same size. The thing is that 1 nanosecond, that's the time it takes for the speed of light, for the light to travel from this end of the paper to the other end of the paper. So this is 200 papers back and forth. So it's just 100 papers. It's basically maybe the outer wall there and back again. That's what we can do in 200 nanoseconds. So it's a very short amount of time. So you understand that the magnitude of the problem here. So how can we implement like operations that can complete in such a short time? So let's start by thinking about clusters of node. And let me start with one extreme. You have some kind of computer here in San Francisco, and you have some other computers in, for example, New York. And if we just look at the light, it takes the light 15 milliseconds to go to New York from here. And it needs to go back again, and then it's usually fiber, and the speed of light is slower in fibers. So that adds to 45 milliseconds, and we were looking at 200 nanoseconds. So this is orders of magnitude too slow. It doesn't work. So let's go to the other extreme. Let's say that we have two Linux boxes that we glue together and wrap some duct tape around, and we connect them with a direct connection. What's happening then? Yeah, well, if you do some tweaks, you can come down to like 40 microseconds. And if you are really, pushing it, you can do busy polling and CPU affinity and maybe reach 30 microseconds. And if you're really expert, I'm not that expert, but you can come down to 25 microseconds. That's still 2 orders of magnitude too slow. 100 times slower than we want our operation to complete in. That's just sending a package. So it's not really possible to even use 2 nodes that are so close together. And then we have switches, because it's very rare that computers sit directly connected to each other. And if you deploy on a like Bluemix or Google Cloud, then they have some kind of software networks that introduces even more delays. So this is not the way forward. So how about having different processes on the same machine? That should be quick, shouldn't it? Well, if you look at it, if you just look at inter-process communications, it's still in the microseconds, in the milliseconds. Actually, it's in microseconds, so it's wrong there. But it doesn't matter, it's too slow. It's 5 times slower than we need. So that is out of the question. And even if you have a context switch, you will ruin your different cache layers and your TLB and your CPU, and that will make things slow. So it's a tricky thing to do. So let's look what we can do within the JVM itself, because I'm talking about Java today. Even just reading from main memory takes about 100 nanoseconds, 100 sheets like this. And that's half our budget. So that is expensive. And if you know a little bit about the Java memory model, even a volatile read is 100 milliseconds, because you're not allowed to cache that. Then if we're on the L3, it's 20 nanoseconds. If we're on the L2, it's 7. Level 1 is 0.5 nanoseconds. And, well, the CPU registers are already there. So here we are coming somewhere. This is the area we want to be in. If we want to have operations that complete in 200 nanoseconds, that are really low latency or ultra low latency. So this is an example of a microservice architecture. It's from the fintech area, where we have at the bottom 4 shards with different strategies. They're supposed to operate on a bunch of papers or information about the sell and buy information coming in. And here you have some kind of gateway and some other controlling stuff. And they all communicate with a high-speed bus. And in order to understand how you should deploy these, you have to understand the hardware we're running on. So this is a multi-core Intel CPU. So here you see the actual CPUs, the ALUs and the logic. And here you have layer 1 and layer 2 caches. And these are the layer 3 caches, and they're all shared between the CPUs. So how can you do this? Well, you can do something like this. You can deploy your application on the silicon. So they can run and they can share information through the shared caches. And here we can talk about ultra low latency. And you can use that. So you see the mapping here. So and if you look at it on a higher level, then of course a server-grade CPU architecture is not really one CPU, because it uses something called NUMA regions. So basically there are several computers within a computer connecting with high-speed buses. So you need to understand this if you want low latency. You can't have a CPU here accessing the memory back here, because that will create additional latencies. It's like a high-speed network, but you don't see it. So we need to invite this guy to the silicon itself. We need to map our objects directly on the silicon to get this kind of speed. Okay, so that was about the in-memory. So how can we make now the in-memory available to our applications? Well, we went for the stream API, and now I'm talking about the standard Java streams that are built in Java from version 8 and forward. And why would it do that? Yeah, because there is a remarkable resemblance between SQL and Java Stream operators. And of course, this is not a random coincidence, because the guys who designed the stream interface knew what they were doing. Is there a laser here? Yeah, doesn't work so well. Okay, so for example, we have where in SQL corresponds to applying a filter to a stream, or count is count, or you can group by is collect grouping by. So there is a correspondence to each and everything you can do with SQL, you can do with the Java stream. And this is something I wrote an article about in Java magazine, one of the recent issues. So in this particular example, there was some instruction on how to use streams instead of SQL. So in this case, it rendered SQL automatically from streams. But the nice thing is that you can also render it not to SQL, but to an in-memory graph. And that can be totally transparent. So you can use exactly the same API and use it for SQL or use it for in-memory. The only difference is that it's perhaps 1,000 times quicker or 1,000,000 times quicker. So, and another similarity is that they use something called declarative constructs. And what is that? That is that we express what we want and not how we want it, and not how it should be done. So in the upper portion, you see a very simple SQL statement. It says that we want to select everything from a film table where the rating is PG-13. It doesn't say how we should do it. The database is free to use any means it can to provide that for us. It can, for example, use an index, or it can, for example, use a cached version of a previous query of the same result, or it can use some other means. We don't care. We only want those films where the rating was PG-13. The same is true with streams. It looks like we're creating a stream, and then for each element we're applying a filter. But this is not the case, because the streams are similar to SQL. We say that we want a stream on this line, but on the next time we say we want another stream that only contains the rating equal to PG-13. It doesn't say that we want to iterate over every element in the stream and then apply the filter. And that is important to understand. And that's why stream can be so fast, because we can look into the stream's own pipeline and we can do optimization. And we can optimize away, like using indexes or using other means to really collapse the pipeline. So that's Speedman. Speedman is two parts. Speedman is one open source version that you can use for an open source database. And you can have a tool, create your data model, and then you can query it using Java streams instead of SQL. So you can remain in a Java world with type safety, parallel database queries, and a lot of other features. And there is another part of Speedman that is in-memory acceleration with ultra-low latency streams. So, Stream ORM, and we've been the third most popular ORM on GitHub, and the in-memory technology. And again, if you run this query, it will look exactly the same if you plug in the in-memory accelerator. So it's the same API. Okay, so let's see where Speedman comes in from a market position. Some frameworks operate here. They can work with enormous amount of data, but it takes a long time. Some other products are operating here. They can have slightly less data, but they can provide a result much quicker. Speedman is here in the nanoseconds, operated on a smaller set of data, but can provide things with much less latency. And we're talking about maybe 10 terabytes and below. So if you have 100 terabytes, you should use another solution. Okay, so let's see a demo, how it works. And hopefully I will be able to show this. Great. So this is a benchmark with two different streams. And I would like to see my pointer. There it is. Okay. So the first stream up there is a very simple stream. It's called filter and count, and that's what it is. So it takes a film, creates a stream, and then filter out everything that is PG-13. This is similar to my example that I showed you before. And you can see this predicate up here. It's like, is PG-13 is the same as film rating equal rating PG-13. So it's nothing special with that. So that's the simple stream, and that's the stream I was talking about. These streams, the object with these streams was that they should be completed in 200 nanoseconds, about that time. And there is a significantly more complicated stream here, which I call complex, which creates a stream, sorts all the elements in a length descending order, skips the first 745, then limits to 5, extracts the film, get rental duration, and then compute summary statistics on those elements. So this is much more complicated. And we're going to benchmark that and see how is a complicated stream performing here. Yes?
It is a stream data, right? Like if we are getting let's say, sometimes we get a 600 data points or sometimes. So here it is looking for the 750 data points and the first point. So if the stream doesn't have that many, what's going to happen? Or if you are getting more data.
Yeah. So the question is, what if I'm cheating here? What if I say that I only had 500 and then skip 7045 and then we'll get a good result? And that's he's a clever guy, so he sees that I'm trying to trick you here, but I'm not doing that. So in this particular case, there's 1,000 films, but these operations are order 1 or order log n, so it doesn't matter if it's kind of 1,000 or 100,000. It will be the same result regardless. But it's 1,000 films in this case, so I will keep into that span. Good question. So let me start this. Well, yeah. So while I'm running it, it takes a few seconds. I will just show you what I'm doing here. This is the Java micro harness framework that's used to be a good thing to do performance tests. So I'm running throughput mode here and not delay, and that's why this is so fast that the framework cannot detect it. It cannot measure such small intervals. So instead I'm using the other way around. I do a lot of threads. I don't do a lot of threads. I do a lot of queries, a lot of streams, and then I measure the duration, and then I invert the result because it can't even measure that small time it is. And I'm only using one thread, otherwise I would be cheating. So now it's ready. So the complex one here is able to complete 400,000 of those streams on my laptop, which is an old, it's 2 years old. I should get a new one, by the way. Okay. Then it will be faster. So that's 400,000, one on a single thread. So that's about 2.5 microseconds. And that's good for a complex stream, I think at least. So let's look at this more simple one. It did 6 millions. So it's even faster than 200 nanoseconds. It's maybe 1.75, 175 nanoseconds. That's quite, it's astonishingly low latency. So this stream was extremely fast. So, and I can show you also the scalability here, because Speedman is using kind of immutable snapshots. So that means that the parallelism is very high. So let me show that. Oh, weird. So I can use the maximum number of threads here, which is, I have 4 CPUs on this laptop. So let's start this one and see how many streams we can do per second. So I guess you have to wait 20 seconds for this is kind of a cliffhanger. Now everything is loaded from the backing database. That takes about 1 second, and then the test starts. So this is the first more complicated stream that we have. Tension builds. Will it work? So this is the second one. You notice they are being faster. So there's a warm-up iteration, and that's because Java JIT compiler kicks in and do some optimizations. So now we can see here that we do 1.4 million of those complex streams on a laptop. And we did 22 million streams of the more simple one on a laptop. So you can imagine what you can do on a server with Xeon processors and maybe 47 or 24 CPUs. So that's what I wanted to show you guys. So let's go back to the presentation. So how is this possible? Well, we use in JVM memory access with a Java Stream API. And streams, they introspect their own pipeline, meaning that before they execute, they look at their own pipeline and see what kind of optimizations they can do. It's like a query planner for a regular database, something like that. And everything is off heap. And why is that important? Of course, you want predictability. You don't want to have 600 billion objects lying around on the heap, because then your garbage collect will kill your application. So it's kind of self-evident that all data is stored off heap. And since we learned that just reading a volatile memory is 100 nanoseconds, everything is snapshots and read-only. So you can create a lightweight snapshot very quickly. You can create hundreds of snapshots, or you can create every second or every hour. It doesn't matter, but they are snapshots. And that's why they can be so quick. And there is also lightweighted off-heap indexing, because, well, if you have all your data off-heap, but if you have your index on-heap, that wouldn't make so much difference anyhow. And our operations are order 1 or order log n. So if your data size grows, the complexity of the operation doesn't grow, or it grows only very slightly. We have collectors that do not create intermediate objects. We don't create Java objects when we collect things. Because if we would, then we will create a big heap, and we will have garbage collect, and then the predictability will go out of the window. We have aggregators that do not create intermediate objects. Same thing there, of course. And since the snapshots are created, we can do a lot of stuff with them, because we know they will never be updated. They will be just discarded, and there will be a new snapshot if we update our data. So we can do a lot of optimizations on them. And of course, we are using our objects very carefully. So the standard escape analysis on Java enable us to actually allocate some of the objects on the stack instead of on the heap. So that will give us performance. Yes?
What happens in the collectors in that, because it doesn't keep the objects, right? So as the objects comes, what happens, and where does the object store?
Yeah, that's kind of secret. But it doesn't create objects. We use another way of keeping them in memory. It's nothing really peculiar, but there is a big object that creates all the sub-objects instead of creating a lot of small objects. That's what I can tell you. So what about a stream? How does it look like? Well, if we take this example, we have film streams and filter rating equal PD13, and we collect them somehow. This is actually an answer to questions, almost. Yeah. So we have a collector that we have did in advanced, to JSON length and title, a function that returns a collector that does this. When the stream introspects its own pipeline, it will see that, wow, I have kind of an index. This is a very simplified picture, but this is how it works on a high level. So it sees that there's an index on the rating, and it will see immediately which objects are PD13, so they will know. It will know where in the memory it will start, so the first one will just go there and collect these things to the collector, and the actual object will never be materialized. So it's using something called in-memory or in-place deserialization. So all the elements and all the columns in an entity can be deserialized in place. And it just continues and it goes on. So it's something of a reversed thing when you compile all these. You lay them out flat in memory, and then you just add stuff on them, and then it's ready. So you don't create an object for each of these, and when you aggregate, you don't create a lot of keys for your object for your keys. For example, if you have composite key of 20 keys, then it's a lot of objects being shuffled around. So you don't do that. Okay, so about scaling out. Well, the good thing is that you can use off-heap memory. You can map that to files. And actually, you don't have to do that in order to save RAM. You can do it as a means of communication between JVMs. So you can have one microservice type 1, JVM 1, and microservice type 1, JVM 2. They can share the same file and map that into memory. So when you start the second guy, you just hand off a reference to a file, and it will have perhaps 1 gigabyte or 1 terabyte of data instantly available. And the operating system will make sure that those pages are paged in, so we don't have to be concerned about that. And of course, we support sharding, so if you have a problem that is sort of contained to a sharding key, you can work with smaller instances if you want. Yeah, so this is a comparison with the off-heap in JVM memory, where we keep off-heap all the time. You see the happy guy. The average latency 100 milliseconds for a compound operation. This was just not one stream, but millions of streams. And if we work with object, it took longer. And especially, this is a concern because sometimes you have garbage collect, and then this guy shows up. You don't want to see this guy. He's bad. We could do, instead of 8 nodes, you can do 2 nodes. Didn't have any major garbage collect because we didn't create any objects. Whereas this has 27 major collections. Could have much less RAM because it's more efficient. Could have much less CPU because it's more computational efficient. And you don't have to spend a lot of heating doing garbage collect all the time. The average utilization was 40%. That means that we only used a fraction of 1 CPU, whereas here you had to use like 20 CPUs. It's much quicker to load, 2 minutes to load this data set, which was almost a terabyte. Whereas it took 28 minutes when you have to create a lot of objects and sort them into maps. And you might know that Java has maps from the beginning, but there are also, like we humans in the middle world, that are good with small sets or medium sets, but they really perform lousy when you have big sets in them. Try creating a stream from a concurrent hash map with 2 million or 10 million objects, and you will understand what I mean. So, low operating cost, high operating cost, happy user, sad users. Very simple. Okay, and this is, I'm going to show you one kind of picture with the objects from the space again. So, if it takes the database 1 second to make a query, how far will the light move? And now, some clever guy will say that it's 3 times 10 to the power of 8 meters, and that's of course right, but is there something else that is the distance from the Earth that it takes 1 second to reach? Exactly, the moon. 1.3 seconds. So that's the distance it takes for the light to go. Whereas if you use the L1 cache, it's 4 inches or 10 centimeters for us from the metric system. So the conclusion is, don't place your data on the moon, keep it in the JVM. And you can use almost any source. You can use open source databases or any of the usual databases, Avro files, binary files, CSV files to ingest data. A guy even wrote a Google Sheets plugin to Speedman, so he can configure his in-data using a Google Sheet. That's funny, I think. You can deploy anywhere. You can deploy on premises, of course. You can deploy in any of the big ones. You can use Docker and Kubernetes. Incidentally, Docker has a feature where you can use affinity to pin down your application on a particular CPU. People have deployed Speedman on Raspberry Pi 3s with good performance. That just shows you the versatility of this. You can use any IDE. Of course, it has integration with them. You can deploy on any Java EE server, or you can use Spring Boot. We see a lot of customers use Spring Boot these days. It's become very popular. And in terms of application API, you can use Java 8, or if you don't use Java, you can use a plugin that generates REST APIs. But that, of course, you will not get 200 nanoseconds. It will take a long time. Vaadin is a plugin for creating user interfaces, and it's using streams. It's a pure Java thing, so you can use Vaadin directly with speedman. And of course, we have released Java 9 support just before Java 1 this month. So, and you don't have to do anything in one big bang. If you have a small problem, use speedman, solve that problem, and move on. You can test this today. You can go to our homepage, go to something called Initializer, and then you can just say what kind of database do I have. And make sure to tick this guy, in-memory acceleration enable, because it was not enabled when I took this screenshot, which was a mistake, but click that. And that's my presentation. So if you have questions now, talk to me. If you don't have time or you want to rush away or want to think about your questions, mail me. And if you have something you want to discuss, I'm offering you, if you mention in-memory computing summit, I can get you 30 minutes free consultation if you want. Or if you don't want that, it's okay. You can mail me anyhow and ask questions. So then I open up for Q&A. Yes?
Does this work as a service of its own, or we insert this into our own microservice and like replace our, let's say, JDBC driver that we depend on and use speedman driver to select straight from the
in your project, you typically have the dependency on speedman, a single dependency with no other transitive dependencies. So speedman becomes a part of your application. And the reason it becomes a part of your application is for speed, because we would have it deployed as a separate process, then it would be slow. So it's kind of what's called scale in. So it becomes a part of your application, and you're using it via the stream interface.
So we don't need to depend, let's say, JDBC driver or any Apache data source or anything, depend on speedman and then use the stream API that speedman gives us.
If you only want to use speedman, then you don't have to depend on JDBC drivers. But if you have your data, your source of truth in a database, then you have to depend on a JDBC driver for that particular database. Like if you have an Oracle database, you have to depend on Oracle 7 JDBC, and then it will pull in the data automatically from the database. And it also, if you remember, I showed this, there was a tool here. Let me see if I find it. It's used to build up your data domain model. So typically, you can do this code, but there is a convenience tool that allows you to just connect to a database and extract all the tables and columns, and you can click here, do mapping, and press this generate button, and you get your complete data model generated for you in Java. And then, of course, you need the connector. If you're using the open source, the connectors are already there, so you don't have to depend on them, but you can override whatever you want. So does that answer your question? Yeah, sure. I'll be happy to. Drop me an email and I can send you a way to find it. Yeah. Sure. More questions? Okay. Thank you, guys. Thank you.